Well, according to Elon Musk, Tesla is now approaching what he describes as the final stage of development for Optimus Gen 3, a robot he believes will become the most advanced humanoid machine ever created. Musk has confidently stated that no existing robot currently demonstrated by competitors comes close to what Tesla is preparing. Yet this bold declaration has raised a fascinating contradiction. While Tesla claims Optimus is nearly ready for commercialization, the number of robots currently performing meaningful work inside Tesla factories remains extremely limited. At the same time, reports suggest Tesla has quietly accumulated hundreds of millions of dollars worth of robot components, enough to support the production of an enormous number of units. This unusual gap between public demonstrations and massive supply chain commitments has sparked speculation throughout the robotics industry. Many observers now wonder whether Tesla is preparing a major technological breakthrough behind closed doors and whether the company is already laying the foundation for a production scale that few people thought possible only a few years ago. Musk has explained that production of Optimus Gen 3 is expected to begin gradually, with manufacturing starting at a relatively slow pace before accelerating dramatically over the following year. Tesla's long-term strategy appears to involve releasing improved versions of the robot on a regular basis, much like software updates or new vehicle models. Each generation is intended to become more capable, more efficient, and easier to manufacture at scale. The shift from earlier prototypes toward a fully commercial design has required Tesla engineers to rethink nearly every major mechanical system inside the robot. One of the most important challenges involves durability. A humanoid robot operating in factories must survive countless hours of repetitive movement, impacts, and heavy workloads without suffering mechanical failures. Solving this problem has forced Tesla to redesign critical portions of the robot's motion system from the ground up. Instead of relying heavily on traditional harmonic drive mechanisms throughout the robot, Tesla has reportedly adopted more robust cycloidal reduction systems in several major joints. These systems provide higher durability, better shock resistance, and improved torque output under demanding industrial conditions. The change is particularly important in areas such as the hips and shoulders, where the robot experiences significant mechanical stress. Harmonic systems continue to be used in lighter applications where their advantages remain valuable, but Tesla appears focused on creating a machine capable of surviving years of continuous operation in real-world environments. This shift reflects a broader philosophy guiding Optimus development. The robot is not being built as a laboratory demonstration. It is being engineered as a practical workforce machine intended to operate day after day in factories, warehouses, and eventually countless other industries. According to Musk, three major challenges define the path toward truly useful humanoid robots. The first is achieving real-world intelligence capable of understanding complex environments. The second is developing hands that can match the flexibility and precision of human hands. The third is mastering manufacturing at a scale large enough to make the robots affordable. Among these challenges, the hand system may be one of the most impressive breakthroughs within Optimus Gen 3. Tesla engineers have reportedly achieved a dramatic increase in component density, allowing many of the hand's actuators to be relocated into the forearm. This design uses tendon-like mechanisms that more closely resemble biological structures, creating a system that is lighter, more compact, and significantly more capable. The result is a substantial increase in dexterity. Previous versions of the robot possessed far fewer degrees of freedom, limiting the complexity of tasks they could perform. The new design reportedly doubles the available movement capabilities, allowing the robot to manipulate delicate objects with far greater precision. Tesla has also integrated advanced tactile sensing technology into the fingertips, enabling the robot to detect pressure and contact with remarkable accuracy. These enhancements could allow Optimus to perform thousands of different tasks ranging from handling fragile materials to assembling highly complex components. Whether lifting industrial parts or carefully managing delicate objects, the robot is being designed to approach human-level manipulation capabilities. The push toward commercialization has also triggered a massive hiring effort inside Tesla. The company is aggressively recruiting specialists in motor design, electromagnetics, manufacturing systems, and industrial engineering. Many job postings reveal a strong emphasis on accelerating the transition from laboratory development to large-scale production. Tesla's goal is not merely to build advanced robots but to manufacture them in enormous quantities while maintaining cost efficiency. This ambition is reflected in the rapid expansion occurring at Tesla facilities across the United States. At Gigafactory Texas, large-scale construction projects continue to reshape the landscape surrounding Tesla's operations. Drone footage and independent observations have documented extensive development activity, including new structural frameworks and expanded industrial facilities believed to support future Optimus production. Foundations continue to be poured, land is being prepared for additional expansion, and infrastructure investments suggest Tesla is thinking far beyond initial production goals. Rather than focusing solely on thousands or tens of thousands of robots, the company appears to be planning for a future measured in millions of units annually. Such extraordinary manufacturing ambitions create another major challenge: computing power. Training humanoid robots requires vast amounts of artificial intelligence processing capacity. Every movement, interaction, and decision-making process must be refined using enormous datasets and advanced machine learning systems. Tesla's answer to this challenge is the expansion of its AI infrastructure. New computing clusters are being deployed with massive power requirements, utilizing large numbers of advanced GPUs to train increasingly sophisticated neural networks. These systems are designed to support vision-based artificial intelligence models capable of helping robots understand and navigate the physical world. Supporting such computational demands requires substantial energy resources. Tesla has therefore invested heavily in energy storage systems around its AI facilities. Large numbers of megapack units are being deployed to store electricity and stabilize energy consumption. The company's broader strategy appears to involve integrating its energy, transportation, and artificial intelligence businesses into a unified ecosystem. By combining battery storage, supercharging infrastructure, custom AI chips, and distributed computing resources, Tesla hopes to create a highly scalable platform capable of training and operating millions of autonomous machines. Another interesting development involves Tesla's efforts to create modular computing systems that can be deployed across existing infrastructure. Patent filings and trademark registrations suggest the company may be working on portable data center solutions capable of utilizing underused electrical capacity at various locations. Such systems could transform Tesla's charging network into a distributed computing platform, helping power the artificial intelligence systems required for future robot fleets. This approach would allow Tesla to maximize the value of existing assets while expanding computational capacity far beyond traditional centralized data centers. All of these efforts ultimately serve one objective: reducing the cost of humanoid robots to commercially viable levels. Many competing humanoid robot programs currently face extremely high production costs, limiting their practical adoption. Tesla believes large-scale manufacturing can dramatically lower prices. The company reportedly aims to achieve a target price range that would make Optimus attractive across multiple industries. Achieving this goal requires a highly coordinated global supply chain involving partners across Asia and North America. To support production, Tesla has strengthened relationships with suppliers responsible for components ranging from precision actuators to advanced optical systems. These suppliers are increasing capacity, establishing new manufacturing facilities, and accelerating production schedules. Some have reportedly entered joint ventures specifically designed to support future Optimus demand. This coordinated effort reflects growing confidence that Tesla is approaching a point where large-scale robot production may become a reality rather than a distant ambition. As development continues, Tesla is expected to use transitional versions of the robot to validate hardware and software systems before finalizing the next major production design. Extensive testing will be required to ensure reliability under real-world conditions. Once these validation stages are complete, Tesla intends to move aggressively toward mass manufacturing. Facilities such as Fremont are reportedly undergoing preparations to support Optimus production at unprecedented levels. The company envisions converting portions of its existing automotive manufacturing footprint into robot production lines capable of producing vast numbers of units annually. This brings us to perhaps the most important question surrounding Optimus today. If Tesla successfully builds hundreds of thousands or even millions of robots every year, who will buy them? The answer may be much broader than many people initially assume. Tesla itself represents the first major customer. Across its factories, the company employs large numbers of workers performing repetitive physical tasks. Many of these activities could eventually be handled by humanoid robots. Material transportation, inventory management, component movement, quality inspections, and various support functions are all potential applications. By deploying Optimus internally, Tesla gains the opportunity to improve productivity while simultaneously refining the robot through real-world experience. Beyond Tesla's own operations lies the vast global manufacturing sector. Factories worldwide face growing labor shortages, increasing wages, and ongoing challenges related to workforce availability. Traditional industrial robots often require specialized workspaces and extensive infrastructure modifications. In contrast, a humanoid robot designed to operate within environments already built for people offers significant flexibility. Manufacturers could potentially introduce Optimus into existing facilities without completely redesigning production lines. Even limited adoption across a small percentage of factories could generate demand for hundreds of thousands of robots annually. The logistics industry represents another enormous opportunity. Warehouses, fulfillment centers, and distribution networks employ millions of workers around the world. These facilities constantly move products, organize inventory, and process shipments. A humanoid robot capable of performing such tasks continuously could deliver substantial economic benefits. If Optimus can operate safely and reliably around the clock, companies may view robot deployment as a highly attractive investment. Large logistics operators managing dozens or hundreds of facilities could become major customers, purchasing thousands of units at a time. Retail environments present yet another promising market. Stores, supermarkets, and distribution centers require constant restocking, inventory movement, organization, and operational support. Labor shortages remain a challenge across many retail sectors, creating opportunities for automation solutions. A versatile humanoid robot capable of performing a variety of routine tasks could help businesses improve efficiency while reducing staffing pressures. Given the enormous number of retail locations worldwide, even modest adoption rates could generate substantial demand. Healthcare and elder care may eventually become some of the most transformative applications for humanoid robots. Many countries face rapidly aging populations and growing shortages of caregivers. Robots capable of assisting with daily activities, mobility support, reminders, and household tasks could provide meaningful assistance to elderly individuals while reducing strain on healthcare systems. Although these applications may require additional technological development and regulatory approval, they represent a potentially massive long-term opportunity. Consumer households may ultimately become the largest market of all. However, widespread household adoption will likely depend on significant cost reductions and continued improvements in capability. Early versions of Optimus are expected to remain relatively expensive compared to typical consumer products. Yet Tesla's strategy mirrors the path followed by many successful technologies. Initial products enter the market at higher prices, manufacturing scales increase, costs decline, and capabilities improve over time. If Tesla successfully follows this trajectory, future generations of humanoid robots could eventually become common household assistants capable of handling chores, maintenance, caregiving, and numerous everyday responsibilities. Despite the excitement surrounding Optimus, significant challenges remain. Building an advanced humanoid robot is only part of the equation. The machine must consistently demonstrate intelligence, safety, reliability, and adaptability in real-world environments. It must be capable of handling unpredictable situations while maintaining performance standards suitable for commercial deployment. Achieving these objectives will require continued advances in artificial intelligence, hardware engineering, manufacturing, and operational testing. Nevertheless, Tesla's actions suggest the company is preparing for a future in which humanoid robots become a major business alongside electric vehicles, energy storage, and artificial intelligence. Massive investments in factories, computing infrastructure, supply chains, and engineering talent indicate a level of commitment rarely seen in emerging industries. Whether Tesla ultimately succeeds in producing millions of robots annually remains uncertain, but the scale of its ambitions is undeniable. If Optimus achieves the capabilities Musk envisions, the project could fundamentally reshape manufacturing, logistics, retail, healthcare, and eventually everyday life. The coming years may determine whether Optimus becomes one of the most important technological products of the century or simply another ambitious experiment. For now, Tesla appears determined to push forward at full speed, betting that humanoid robots will become the next great platform for global automation.